Okay. Okay. Hi, everyone. So I'm Loïc Trompet. I'm working here at Bureau. I'm not going to speak that much about dust. I'm going to speak about temperature, which is some kind of side quest in the roadmap project. So why are we interested into retrieving temperature? Well, there is one part of it which is to improve the retrieval of minor species. So there is, for example, this paper that was published this year by Shohei Aoki, where he was finding a depletion in carbon-13, but he was also reporting strong variability of his retrieval with respect to temperature. And there is another some other tests which are being made for the moment by Ariana Picciali with ozone, and again she sees again that for her spectral signature of ozone, she sees that there is also some variability with the temperature, which are important to take into account, and so we need to have the best possible temperature for the retrieval of those minor species. So now to come back a bit more to aerosols. Well, temperature, can also give us some information of where some molecules can start to condense. And I'm going to speak, in fact, at the end of this presentation, I will show some profiles of temperature where we are quasi sure that there is some CO2 ice clouds there. So those were found a long time ago. We are not discovering anything new, but we are continuing the report about the CO2 ice clouds in the atmosphere of Mars. And well, this CO2 ice cloud I'm going to discuss is about those that we found in the mesosphere, so where we have the coldest temperature, and where in fact the temperature can even decrease with the application of so with the help of thermal tides or gravity waves. So now to speak really a little bit about dust. So there was an explanation yesterday Zachary gave, I think. So yeah, dust and temperature are related. We know it from the dust cycle. So close to perihelion, there is a more important solar flux that hits the surface. There is an injection of dust in the atmosphere. This dust hit the atmosphere. So an increase of the temperature, which increase the scale height, and what we see, for example, in CO2 density, we see well this increase of the scale height, so an increase of the density. And here is a large increase because we are looking at 75 kilometers of altitude. So now I'm going to explain how we retrieve temperature. So for this, I will need to explain a bit more about NOMAD. NOMAD is one of the 4 instruments on board TGO, Trace Gas Orbiter. So yesterday you had some results from Yannick and from Zachary, and those results were coming from measurements from the UVIS spectrometer, and the temperature that I'm retrieving are coming from measurements from the SO channel. And the SO channel stands for solar occultation. So what is solar occultation? Well, we are scanning the light passing through the atmosphere, and we are looking at where the light has been absorbed by, so where there are some spectral signature from molecules. And so each molecule has its own spectral signature, and the spectral signature is dependent on density of the molecules. So I'm going to speak a bit more about the NOMAD-SO channel. So the 2 main components of the SO channel are an echelle grating that disperses the light. This light is dispersed in different diffraction orders. Here you have the x-axis, which is wave numbers. So you have different diffraction orders corresponding to different wave numbers, but in fact, all those diffraction orders are on the same position on the detector, so we need a filter. The filter is an acousto-optic tunable filter, which is a nice device. So it's a crystal where you apply a pressure wave on the side, and this pressure wave will interact with the photon, with the light, and only a part of the light can pass through the crystal. And well, the EOTF transfer function has a full width at half maximum that has been tuned to be very close to the full width at half maximum of the diffraction orders. And well, so that's how we can select one diffraction order at a time. So for the calibration, so here you have one diffraction order, so you recognize the shape. What you see here is that you have different spectra that have been taken at different tangent altitudes, a different slant path. And well, when you go deeper into the atmosphere, and then the lines start to increase as there is an increase in density. And what you see also when you get deeper into the atmosphere, in fact, the spectra, the broadband spectra start to reduce, and this is due to the aerosols. To calibrate those into transmittance, so it's very simple. We just take a spectrum outside the atmosphere where we are sure that there is no spectral signature, and then we divide each of those spectra by the spectrum. So this representation that represents better just what I just said. So this was phosphor. This was the predecessor of NOMAD-SO. So you see, we get deeper into the atmosphere. This was made by Arnaud Mailleux, and you see that so the lines start to appear, and there is this decrease of the baseline as we get deeper into the atmosphere. And the spectral signature here was HCl. There is also HCl on Mars. So Tor was on board Venus Express. But there are different diffraction orders. I'm going to speak about two diffraction orders here. About diffraction order 148 that scans in fact those lines. So the lines of CO2. Maybe you will see it better on the screens there behind. The lines of CO2 are provided here in orange. Then you have water. Water is everywhere almost. So we in the retrieval I have to take into account the fact that possibly there is some water lines in the spectra. So I will be using diffraction order 148. This one is in fact for the mesosphere, and diffraction order 132, which is this very small band, and this one is adequate to scan CO2 in the troposphere. The retrieval method is split in 3 steps. This is very similar to what was done for SPICAM in the paper of Eric Kemmerer et al. In 2006. So first, the spectral signature is converted into slant column, because in fact what we see in the spectra is the effect of the whole slant column. And so those spectra are inverted independently. To do that, I use a radiative transfer code, which is azimuth. So azimuth is a transfer code that has been used by many people. It has been compared by other people, so this is good. So once we have the slant column, those are converted into CO2 density, and this is where regularization is applied. It's necessary to apply some regularization here because this is an ill-posed problem. This is an inverse problem, and we'll see later there is some regularization which is necessary. Then once we have the density, we can convert it into the pressure and then temperature using the hydrostatic equilibrium equation. For the spectral inversion, so I'm not going into the details, but in fact, so you see that what we have to compute here is line shape, and that line shape in fact will be dependent on pressure and temperature, but the temperature and pressure are varying with height in the atmosphere. And while Azimuth is using some assumption, but it's working very well for this. Azimuth is making a great job at computing the slant column. So the slant column is the is the integration of the density along the slant path, and we can recompute this into this formula, this very simple formula, where in fact the slant column is equal to k multiplied by the density, and where k here is the Abel transform. So we have the slant column, but what we want is the density now. So what we have to do is to inverse k. So if you inverse k, and if you forget about this term here, you have some kind of the pseudo inverse of k. And if you do that, in fact, you get some profile with high spurious peaks. So here I'm showing not the density, but the temperature, because we see those spurious peaks well better into the temperature profiles. And well, those spurious peaks are coming from the fact that we have an ill-posed problem here. In fact, this is due to the fact that the solution is very unstable with respect to the measurement. So if you have a small modification of the measurement, this will lead to a large modification in the solution. So what we do is we use a Tikhonov regularization, where we have to fine-tune a regularization parameter, which is lambda here. And to do that, where we are computing something like 1,000 of those inversion, this is very fast, so that's not a problem. And we minimize this function. So what is this function? It's the sum of the smoothing error. So where you have here is the averaging kernel. A is the averaging kernel. So if you have done already retrieval, you for sure have already heard about the averaging kernels. So the averaging kernel is the application of this J matrix to the forward model, which is here just the Abel transform. And well, this term will be an increasing function. And well, the norm here, we can see it's an increasing function of the parameter lambda. And so why is it an increasing function of the parameter lambda? Is because, in fact, this averaging kernel is getting further away from the identity matrix. And then the other term is the first moment method applied to the covariance over the slant columns. And this is a decreasing function of the parameter lambda. And so when you sum the both, well, you get a minimum. And this minimum is your best smoothing parameter. So this doesn't come out of nowhere. This has been proved by a mathematician a long time ago. And we see, in fact, here, so in this case, so if you use a too small regularization parameter, you will still keep those spurious peaks. If you use a parameter which is too high, in fact, you get this one, which is, in fact, what seems to be the true variability of the profile seems to change, to not be the correct one. In fact, we see this better in this example. In fact, if you use a smoothing parameter of 10, then you see the profile getting far away from what we expect. And here, the best smoothing parameter was 0.63. That's the red one in this plot. So once we have the local density, we can derive a difference of pressure, and we do this using the hydrostatic equilibrium equation. It's simply an integration of this formula. There is another way to get this by something that looks more like an analytical form of this formula. But here we have to play with exponential integrals. Those are tabulated, and I'm using Python. It's extremely fast to get a value for this. And once we have the difference in pressure, we can get the difference in temperature, and we can recompute a full profile of temperature. Here are some examples of those profiles. So this is for Martian year 37. We are in Martian year 37 now. I made this plot in the end of July, so I stopped this somewhere in the end of July. In fact, all the profiles are done, are retrieved automatically now. I do not have even to press a button. And here you have the profile for diffraction order 148, and here the profile for diffraction order 132. Why am I not using diffraction order 148 to get a full profile up to, well, we wouldn't go to the surface, but up to 10 kilometers? Well, there is a problem. and this problem is called saturation. So what you see here in those plots is the equivalent width. So what is the equivalent width? The equivalent width is the area of a line. So you have the baseline, you have the line, and so the equivalent width is simply the area. And well, the equivalent width is a linear function of the logarithm of the density. And here, instead of the logarithm of the density, I've been using the tangent altitude, it's the same. Well, you see that at the beginning, when we start to see the line, well, you have a linear function between the equivalent width and the logarithm of the density. And then after a few kilometers, what you see is that, well, there is still an increase of the density, but there is no more increase of the, there is a very substantial increase. There is a very small increase in the equivalent width, a very small increase in the line. So in fact, when I make some tests, when I try to retrieve the density from diffraction order 148 here, I get some very wrong values. And this is due to the fact that, in fact, we don't have enough information here to really derive the density. So there are ways to palliate this. But well, in fact, we don't have information here still. So there are ways that we could use, but well, I'm not really confident in those ways. The thing is that with NOMAD, we have a broad spectral range, so we can use another diffraction order with other lines of CO2, where we are still in the linear regime between the equivalent width and the tangent altitude. And this is why I'm using two different diffraction orders to get most of the information that we could get between 10 kilometers and 100 kilometers. So those profiles are provided to other people. And well, those other people wants to have a full profile, not just some parts of it. So what I'm doing is that I'm smoothing slightly the profile. So here what you have in blue is the profile as retrieved. In orange is the profile as provided by a GSM, by GEMMARS. And in green is the combination of the two. And this is what I provide to the colleagues. So a small advertisement now to Vespa. So all the data that we published are on Vespa. So Vespa is a portal where you can find a lot of data about planetary science. And there are really a lot of different kinds of data. You have data from lab, data from experiments around planets. Well, if you haven't heard about Vespa, I believe that it would be good that you go and have a look there, and maybe you will find some data that you will be interested in, or maybe it would be interesting for you to provide your data through that portal. So now I'm going to show some comparison, not with other datasets, but with between two ways to get the temperature. So I've shown one way to get the temperature using the sun column and the isostatic equilibrium, but in fact, some lines of CO2 are very dependent on the temperature, and we see it here. So the CO2, the main CO2 lines in diffraction order 148, and you see that those ones are not that much sensitive to temperature, while the lines in diffraction order 149 are very sensitive about temperature. So what I need to say as well is that well, the fit of the temperature was implemented by Bastien Vispoul. It was a big job, which is now I see helping a lot. So Bastien Vispoul was working. It was in the framework of the roadmap project. Now he's working in the University of Namur. So I will show some comparison for diffraction order 148 and 149. So what you see here in blue is the fit of the sun column and the temperature, and in orange is just the fit of the sun column. And you see that the value above 50 kilometers are very similar. In fact, the value of fitting just the sun column is slightly better. I believe that this is due to the fact that we are trying to fit temperature to some lines that are not very sensitive to temperature. And well, also try to fit below, so where we have saturation. Why did I do that? It was to see if the fit of the temperature would improve the retrieval in the saturation part, and this is not at all the case. In fact, you see that both the temperature and the sand current gets completely crazy there. For diffraction order 149 is completely different. In fact, you have still in orange the retrieval of just the sand current, and then in blue sand current plus temperature. And well, you see that you have those period peaks that are much more important when fitting just a sand current. So those are that meaning that the problem is more ill-posed when we are fitting just the sand current. And when we fit the temperature in addition, then the profile is better, and we can get lower into altitude. So when we look at some spectra, so on the left is a spectrum where we fit only the slant current. On the right is when we fit slant current plus temperature. So you see in orange is our best fit, and in blue is the data. So you see in the residual between the two that you still have some bad residuals between the two, and when you feed the temperature, then those residuals in the lines are disappearing. So there was an improvement by feeding the temperature in diffraction order 149. So now I'm going to show some comparisons with other datasets. So when we have some dataset, we want to compare to others to see if what we get is correct, and what we want to compare to for the temperature in Mars. Well, we want to compare to the Mars Climate Sonder because it has been around Mars since 2006, and well, here, in fact, I found 117 profiles that could be compared. So they are within this collocation criteria, which is the same than the one in Garlet et al. 2022. And where we see that the average difference is very small between the two, while the average absolute difference is quite large. It's larger than the uncertainties of the two data sets. So the difference between those two numbers is that, well, the average difference, where, for example, if you have a value of SO which is larger than MCS, and then later on you have a value of MCS which is larger than SO, then those would compensate. While the average absolute difference is, while all difference is taken into account positively. So why do we have a so important average absolute difference here? Well, when we look at the profile, well, we see that in fact it seems like MCS is a smoother version of the SO1. I forgot to say that here, in fact, I still smoothed SO profile to get to a vertical resolution of 5 km. So the vertical resolution of SO is between 1 and 3 km. But still, there could be some discrepancy due to the difference in the vertical resolution, and also as well, there could be a discrepancy due to this collocation criteria. If I reduce this collocation criteria, then very fast we don't get any profile anymore to compare. So I made this comparison as well with diffraction order 132. So this was for the altitudes above 50 km. 132 is very similar results. There are less profiles to compare. And I made the same comparison, but with another instrument, which is on a trace gas orbiter. So what is good here is that this instrument, so the near channel, is pointing to the same direction as the SO. So they can be measuring together, and those are actually simultaneous measurements. And here we see that the average difference between near and SO is around 5 Kelvin. So on average, SO is 5 kelvins higher than near. Or near is on average 5 Kelvin lower. And the average absolute difference is 6.7 Kelvin. So it's still high values of differences, but you see that the difference between those two values are not that large. So possibly the difference that we had with MCS could come to the fact that where we are comparing collocated profiles, but not really simultaneous profiles. The Hermas probe was different. So I made the same analysis with diffraction order 132, but there are only 9 profiles. The values are very similar. I made also a comparison to SES mirror. The problem with SES mirror is that it's pointing to another direction, so we are not comparing. We are not measuring simultaneously, but when we look at all the values at specific altitudes, when we see that the comparison looks good. There is no value I can really derive here because I would need to fit those two curves, and it's quite difficult. So now I'm going to show a very few results. So the one I like is this one. So in fact, there are some time and location where we can get some profiles that are very close in solar longitude and very close in latitude and in local time. And you have all those profiles here. So above is for the northern hemisphere, below is for the southern hemisphere. So you see the difference, maximum difference between the profiles here. Well, you see that for the bins of profiles that are between 7 hour and 9 hour in local solar time, within around 70 kilometers, we see this kind of variations, and only between those local time. So when we look at those points as a function of longitude, and we see this kind of curve that quite reminds us about possibly thermal tides, and believe that this one doesn't correspond to this one. But yeah, so on average for all those where there was some of those thermal tides, and I was fitting the amplitude and the phase. And for the amplitude, I was finding that there was a predominance of wave number 1, which was 10% of the background temperature, and a remaining wave number 3, which was around 5%. I need to say as well that all those profiles, all those bins of profiles could be taken only at 60 degrees, either 60 degrees north, either 60 degrees south. Well, why do we have those appearing only at those local time? This is still something I do not understand. It could be a bias in the data, but then we would see it as well, in fact, between 3 p.m. and 5 p.m. And this is not the case. So the only way to have better knowledge about this, I believe, is to compare to GCM. So now I'm going to show some profiles of temperature, which are here and which are well below the limit for CO2 condensation. And those profiles correspond to strong decreases into the baseline of the spectrum. In fact, there are many more profiles that I could show here, but they do not always lead to a strong decrease of the baseline. And well, here are all the data, all the profiles where we are really seeing that those could be CO2 ice clouds, mesospheric ones. So there were 2 in Martian year 35, 2 in Martian year 36, and now we have 6 in Martian year 37. In fact, this is due to the fact that the coverage at the equator was better in Martian year 37. And for the location of all those profiles, then they are not where we do not expect CO2 ice clouds. So they are they are close to the equator and between meridian and 150 degree west. So where already CO2 ice clouds were reported, and as well in this region. So those are regions where there are strong topographic variations. Okay, I will stop here. I believe I've shown all what I wanted to show here for this workshop. Here is a summary. So all the profiles that are derived are done automatically. Temperature is important. So this was from the work from other people. So for carbon monoxide and for ozone, temperature is important to derive proper density. There are 2 main ways to retrieve the temperature, and one is better for one diffraction order, and the other one is better for another diffraction order. The comparison to other data sets looks good, I would say. The temperature at the thermometer show many variabilities. I've shown only a few examples. We are also looking at gravity waves, not shown here. What would be nice to do for the next is to compare to the data of Zachary, probably. Continue the test, but this is a very nice tool to be able to feed the temperature directly on the spectra. I would like to continue the test on that. Continue the comparison to other datasets. This is interesting, and it would be nice to have some kind of harmonized dataset of temperature of the atmosphere of Mars. Well, and continue the analysis of thermal tides and gravity waves. And I will stop here. Thank you for your attention.
Thanks, Loïc. I have one quick question and the other one a comment. So the quick question is, when you provided the temperature profiles with the GCM at the top, do you flag somehow the vertical points where the GCM is used for?
In the file that I provide, yes.
Okay, so they are flagged. People
yes.
know when the GCM.
So there is all the information. There is the profile as I retrieve them. There is the profile which is smoothed with the and then so I provide all the uncertainties with all this. So everything is in the file that I provide.
Okay, and the comment is when you compare to the ACS near infrared, when you calculate your averages, do you take the uncertainties into account? Because I noticed then when if you consider uncertainties, that the differences are not that striking. Sometimes your profiles are within the error bars of ACS.
Yes, most of the time it depends. There are some like this, like these ones, but really this value is probably an extreme bound of what what would be really the comparison. I believe this one might be too low, and this one might be too high, and the choice is somewhere in between those two.
As usual.
Yeah.
I have a couple of questions. The first one is from the first part of what you showed. So you have this regularization step, and I'm not sure if I understood. Do you have to recompute the right lambda for each retrieval, or do you have a reference value which you got from?
No, I recompute it for each value because this is dependent. So the regularization is dependent on the field of view of the instrument, which is slightly changing, not that much. It's changing with the vertical sampling. The vertical sampling can change with respect. It's a function of latitude actually, and this will change the regularization. In fact, the real positiveness of this comes from the uncertainties, and the uncertainties are also changing. So you need to fine tune this.
On each time, and
so,
in each case, it's always a minimization of.
Yes.
Do you have any idea? Because on the example here, it's quite sharp here. The correct lambda, I guess, is the minimum.
Yes. So in most of the cases, it's like this. There are some cases where it doesn't work, and those are quite hard. But those are when, in fact, so here, in fact, it's highly dependent on the uncertainty you provide. If you have a bad knowledge of your uncertainties, this is not going to work. But you know your vertical, so you know what you expect as a vertical resolution, right? Because the vertical resolution will be dependent on your field of view and the vertical sampling. So you see that you know that this would be the lowest result. And you know as well that this term should not be higher than this term. Otherwise, you give more information from the smoothing part than from the information.
The other question is, when you compare the two ways of retrieving temperature, I don't know if you can show it again, because I'm not sure what the take-home message was.
Yeah, it was a bit. So for diffraction order 148, which is this one, in fact, the lines are weakly sensitive to the temperature. And when I try to feed the temperature, I get less good result than when I do not try to feed the temperature. My understanding of this is that we are trying to fit a parameter on data which is not that much sensitive over that parameter. And there is a problem. So you are improving your model.
It was worth trying, but in the end, you don't.
In the other one, so in this one, because we have a lot of, so we are measuring 148, but we have also a lot of measurement for 149. And so for this one, it's absolutely necessary. The results I get with us taking into account the fit of the temperature is very bad. We need to fit the temperature, and we see it in the spectra, it's obvious. You need to fit directly because those lines are extremely sensitive to temperature. So it depends. So here it's a Q branch with some P and R branch with very low J value, and those are weakly sensitive to temperature. Those are high J value, so it's transition from higher population, and those are very sensitive to when you have an increase of the temperature, then those will be increasing too.